Now, in this lecture, we'll answer on two questions. In the first question, we'll find out the radius of this circle that is inscribed by the right triangle, triangle ABC. And in the second question, we will find out the area of the blue right triangle, triangle DCB, that is inscribed by the quarter circle. So we start with the first question. In the drawing, we have the right triangle, triangle ABC. We know that angle ABC equals to 90 degrees, side AB equals to 8 units, and we also know that side BC, the hypotenuse AC, the length of those two sides of the right triangle ABC are integers, and we want to find out the radius of this circle that is inscribed by the right triangle, triangle ABC. So first of all, we will define the length of side BC as A. BC equals to A units according to our definition, and we will define the length of the hypotenuse that is AC as B. That is to say, the hypotenuse AC equals to B units in its length. Okay? And then we will implement the Pythagoras theorem on the right triangle, triangle ABC. According to the Pythagoras theorem, in the right triangle, triangle ABC, by PT is the relation of Pythagoras theorem. So according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is AC, so the square of the hypotenuse is AC squared, and it is equal to the sum of the squares of the perpendiculars. This is to say it is equal to AB squared plus BC squared. I repeat again, according to the Pythagoras theorem, in the right triangle, triangle ABC, AC squared equals to AB squared plus BC squared. AC equals to B according to our definition, therefore AC squared is B squared. That is equal to AB squared. AB equals to 8 units, therefore AB squared is 8 squared, that is 64, plus BC squared. BC equals to 8, so BC squared is 8 squared. So in conclusion, we found out that according to equation number 1, we found out that B squared equals to 64 plus A squared. Here we subtract A squared from this equation, equation number 1, and we get that according to equation number 1, B squared minus A squared equals to 64. Here we will use the algebraic identity that states that B squared minus A squared equals to B plus A times B minus A. Okay, so we can substitute B squared minus A squared by B plus A times b minus a, and it is equal to 64. Okay? So according to equation number 1, b plus a times b minus a equals to 64. So here we know that according to what is given us in the question, AC and BC are integers. AC or BC are integers. But according to our definition, AC equals to B and BC equals to A. That is to say, B and A are integers. And because of the fact that A and B are the lengths of the right triangle ABC, so A and B are lengths, and therefore they must be positive numbers. They must be positive. Okay, they must be positive. So we actually found out that A and B are positive and also integers. That is to say, we can conclude from those two things that A and B are positive integers. Okay, so we can conclude from it that A and B are positive integers. So A is positive integer and B is positive integer, therefore B plus A will be also a positive integer. And we know that B is the hypotenuse of the right triangle ABC, therefore the hypotenuse B is always greater than the perpendicular. So B must be greater than A. If we subtract from this inequality A, we get that B minus A is greater than 0. That is to say, B minus A is a positive number, and because of the fact that B and A are positive integers, it means that B minus A, that is a positive number, they must be also positive integers. So B minus A, it is also a positive integer. And it is obvious from the fact that B and A are both positive integers that B plus A, it is for absolutely greater than B minus A. Why? Because when you add two positive integers to each other, they must be greater than when you subtract one by the other. So B plus A must be greater than B minus A. So here, according to equation number 1, we actually found out that B plus A times B minus A equals to 64. And we already found out that B plus A is a positive integer and B minus A is also a positive integer, and B plus A is greater than B minus A. So which possibilities we have that when you multiply two positive integers by each other, the result will be equal to 64. Actually, there are not a lot of possibilities. The first possibility is that b plus a equals to 1 and b minus a equals to 64, and 1 times 64 is 64. The second possibility is that b plus a equals to 2 and b minus a equals to 32, and the multiplication of the two numbers, 2 times 32 is 64. The first possibility is that b plus a equals to 4, b minus a equals to 16, and the multiplication of two numbers, 4 times 16, will be equal to 64. The fourth possibility is that b plus a equals to 8, while b minus a also equals to 8, and 8 times 8 is also 64, of course. The fifth possibility is that b plus a equals to 16, b minus a equals to 4, and 16 times 4 is also 64. The sixth possibility is that b plus a equals to 32, and b minus a equals to 2, and 32 times 2 is 64. And the last possibility, that is the seventh possibility, is that b plus a equals to 64, b minus a equals to 1, and 64 times 1 equals to 64. So we have 2, 4, 6, 7. We have 7 possibilities for two numbers that are positive integers, and when you multiply one by each other, the result is 64. Okay, but we already found out that b plus a must be greater than b minus a. That is to say, the first column must be greater, that is b plus a, must be greater than the second column, that is b minus a. But because of the fact that 1 is not greater than 64, this is not valid possibility. We cancel this possibility because b plus a must be greater than 64, and 1 is not greater than 64, and 2 is not greater than 32. Therefore we cancel this possibility. 4 is not greater than 16, therefore we cancel this possibility. 8 is not greater than 8, therefore we cancel this possibility. 16 is greater than 4, therefore this is one possibility that is correct, true possibility. And we also have here 32 is greater than 2, therefore it is good possibility, and 64 is indeed greater than 1, that is also a good possibility. Okay, so we have only 3 options that left for b plus a and b minus a. Those 3 options, 16 and 4, 32 and 2, and 64 and 4. In the next step, we will add the two numbers together in order to find out the result. So what is the result of b plus a plus b minus a? If we add the two numbers together, the result will be b plus b is 2b, and a minus a is 0. So the result of adding the two numbers together is 2b, that is an even number. 2b is even number. That is to say, when we add the first number to the second number, the result, the first number to the second number, the result must be an even number. Here 16 plus 4 is 20. 20 is an even number, so this is a good possibility. 32 plus 2 is 34. 34 is an even number, therefore it is a good possibility. But 64 plus 1 is 65, that is an odd number. It is an odd number, therefore this possibility isn't correct possibility. We cancel this possibility because the addition of the two numbers must be an even number, and this is an odd number. So we left only with two possibilities for b plus a and b minus a. b plus a will be equal to either 16 and b minus a to 4, and the second possibility is that b plus a equals to 32 and b minus a equals to 2. Okay? So we write down the two possibilities here. We actually found out that according to the first possibility, b plus a equals to 16 and b minus a equals to 4. I repeat again. The first solution is that b plus a equals to 16 and b minus a equals to 4. It is 4 here. b plus a equals to 4. And the second solution is that b plus a equals to 32 and b minus a equals to 2. Okay? So we will add the two numbers together and we will get that here b plus a plus b minus a, and we will get that here b plus b equals to 2b, and a minus a is 0, and 16 plus 4 equals to 20. So in conclusion, we found out that 2b equals to 20. Here we divide this equation by 2, and we get that b equals to 20 over 2, that is 10. So we found out that b, the hypotenuse b, equals to 10 units. And what is the value of a, that is the perpendicular? According to this equation, b plus a equals to 16. We subtract b from this equation and we get that a equals to 16 minus b. So a equals to 16, and we already found out that b equals to 10. So we substitute b by 10. So a equals to 16 minus 10, that is 6. So we found out that a equals to 6 units. So in conclusion, we found out that the perpendicular a equals to 6 units, and the hypotenuse b equals to 10 units, and the third side is given us, that is equal to 8 units. And according to the second possibility, here we will add the two equations together. B plus b is 2b, a minus a is 0, so 2b equals to 32 plus 2 is 34. So we found out that 2b equals to 34. According to the second solution, we'll divide this equation by 2, and we get that b equals to 34 over 2 is 17. Found out that the hypotenuse b equals to 17 units, and according to this equation, b plus a equals to 32. b plus a equals to 32. Here we subtract B from this equation, and we'll get that A equals to 32 minus B. A equals to 32 minus B, but we have already found out that B equals to 17, so we substitute B by 17, and we get that B equals to 32 minus 17. So A equals to 32 minus 17, that is to say it is equal to 15. So in conclusion, we found out that A, the perpendicular A equals to 15 units, and the hypotenuse B equals to 17 units. So I will draw the two triangles together, and we will see how to find out the radius of the circle that is inscribed in those two right triangles. So the first triangle, we know that here A equals to 6 units and B equals to 10 units. Okay, here A equals to 6 units, B equals to 10 units. One side equals to 8 units, it is given us the question, so we write here that this side equals to 8 units, and this side equals to 6 units, and the hypotenuse AC, it is equal to 10 units. And actually, so this is a right triangle, triangle ABC. Side AB equals to 8 units, side BC equals to 6 units, and the hypotenuse equals to 10 units. Inside this right triangle, triangle ABC, we have a circle that is inscribed by this triangle, triangle ABC. And we actually want to find out the radius of this circle that is inscribed by triangle ABC. So here we are looking for the radius that is equal to capital R. We want to find out the radius of this circle that is described by this triangle. And the second solution to the question is that we have another right triangle, triangle ABC. In this right triangle, triangle ABC, we know that side AB equals to 8 units, it is given as the question. We just found out that side BC equals to 15 units, and the hypotenuse of the right triangle ABC equals to 17 units. And inside this right triangle, triangle ABC, we have this circle that is inscribed by the right triangle, triangle ABC, and we want to find out the radius of this circle. Okay, so in the next step we will find out the radius of this circle. We have two solutions that are possible here, and we'll find the radius of the circle that is described by those two right triangles in each case. Okay, so in order to find out the radius of this circle that is described by triangle ABC, here we have a triangle ABC that could be any triangle. Inside this triangle, the right triangle ABC, that could be any triangle, we have this circle that is described by this by triangle ABC, and we want to find out the radius of this circle. So here, first of all, we define the length of side AB as A. We will define the length of side BC as B. and we define the length of the hypotenuse AC as C. Okay? I repeat again, in the right triangle ABC, side AB equals to units in self, side BC equals to B units in self, and side AC equals to 3 units in self. Inside this right triangle we have this circle that is described by triangle ABC. So here we have rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. We define the center of this circle as O. We define the point of tendency of tangent BC with this circle as M. We define the point of tendency of tangent AB with this circle as N. And we will define the point of tendency of tangent AC with this circle as L. Okay? I repeat on rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So here OM is the radius of the circle because it starts from the center of the circle, that is to say from point O, and ends at point M, that is the point of the circle itself. So here we have the radius OM that is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent BC in this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MO. So if BC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. Here we'll join points N and O together by a straight line. Point O is the center of the circle, point N is the point of the circle itself. Therefore, O1 is the radius of this circle, that is equal to capital R. So here we have the radius ON that is drawn to the point of tendency. That is to say, it is drawn to point N, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. So if AB is perpendicular to NO according to rule number 1, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Okay? So actually, we found out that in quadrilateral NOBM, we have 1, 2, 3 right angles. And the sum of 3 right angles is 90 times 3 is 270 degrees, plus the size of the fourth angle, that is actually angle NOM. In total, the sum of those 4 angles must be equal to 360 degrees. If we subtract 270 degrees from the equation that we created, we will get that the missing angle, angle NOM, equals to 90 degrees. So this angle is the right angle that is equal to 90 degrees. So actually we found out that in quadrilateral NOBM we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle. So we relate to quadrilateral NOBM as a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, MO equals to BM. MO equals to BM, but we already found out that MO equals to R, therefore BM will be also equal to R. Likewise, according to the rule that the opposite sides of a rectangle are equal to each other, we get that OM equals to NB. OM equals to NB, but we know that OM equals to R, therefore NB must be also equal to R because of the fact that they are equal to each other. So after we found out that quadrilateral NOBM, it is not a rectangle but a square. Then we find out the length of line segment AN. From the drawing, it is very easy to see that AN equals to AB minus NB. Again, AB minus NB equals to AN. So that is to say, AN equals to AB, that is A, minus NB, that is R. So in conclusion, AN equals to A minus R. Likewise, we find out the length of line segment MC. From the drawing, it is very easy to see that MC equals to BC minus MC. Again, BC minus MC, and BC minus BM equals to MC. Again, BC minus BM equals to MC. So BM equals to BC, that is B, minus BM, that is R. So in conclusion, BM equals to B minus R. Okay. In the next step, I will present to you rule number 2. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. I repeat again, the lengths of two tangents from a common external point to a circle are equal. So if we focus on the common external point, point A, from the common external point, point A, we have two tangents to the circle, tangent AN and tangent AL. And according to rule number 2, they are equal to each other. So AN equals to AL. But we have already found out that AN equals to A minus R, therefore AL must be also equal to A minus R. AN must be also equal to A minus R. So AN equals to A minus R. In the next step, we'll focus on the common external point, point C. From the common external point, point C, we have two tangents to this circle, tangent CL and tangent CM. And according to rule number 2, they are equal to each other. So CM equals to CL. Okay, CM equals to CL from one side, but we already found out that CM equals to B minus R, therefore CL must be also equal to B minus R. So in conclusion, we found out that LC equals to B minus R and LA equals to A minus R. And according to our definition, the hypotenuse AC equals to C units. So we can write down here that AC, from the drawing it is very easy to see that AC the hypotenuse AC equals to AL plus LC. Repeat again, AC, the hypotenuse AC equals to AL plus LC. But according to our definition, AL equals to C, so we substitute AL by C, and it is equal to AL, that is A minus R, plus LC, that is actually B minus R. So in conclusion, we found out that C equals to A minus R plus B minus R. So C equals to A plus B. Minus R plus minus R is minus 2R. Here we will add to this equation 2R, and we'll get that 2R plus C equals to A plus B. Here we'll subtract C from this equation, and we get that 2R equals to A plus B minus C. Here we divide this equation by 2, and we get that R, the radius of the circle that we are looking for, the radius of the circle that is actually inscribed by triangle ABC, the right triangle ABC, equals to A plus B minus C over 2. Okay, so we found out the formula to find out the radius of any circle that is inscribed by a right triangle. Okay, so we'll use this formula in order to find out the radiuses, the radii of the two circles that we found out in our solution to the question. So according to this formula, the radius of this circle that is described by triangle ABC will be equal to A plus B, that is the sum of its perpendiculars, minus C, that is the hypotenuse, over 2. Okay, so we find out the radius of this circle that is described by this triangle, triangle ABC. The radius of this circle will be equal to A plus B. A is 8, B plus is 6, so it is 8 plus 6 minus C, that is 10 over 2. 8 plus 6 is 14, and 14 minus 10 is 4, so it is 4 over 2, that is 2. So we found out the radius of this circle that is inscribed by the right triangle ABC equals to 2 units. Okay. In the next step, we'll find out the radius of this circle according to the same formula. The radius of this circle will be equal to the sum of its perpendiculars, that is 8 plus 15, minus the hypotenuse, that is 17, over 2. So actually 8 plus 15 is 23, and 23 minus 12, and it is actually, here it is minus the hypotenuse, that is AC, is 17. AC is the 17 here. So it is 23 minus 17 over 2. 23 minus 17 is 6, and 6 over 2 is 3. So here, in this right triangle, we have this circle that is described by the right triangle ABC, and this radius, the radius of this circle, equals to 3 units. So in conclusion, we have two solutions to the question. The two solutions to the question is that the radius of this circle that is described by this triangle ABC, it is equal to either 2 units or 3 units. Okay, and that is the answer to the first question. So finish with the first question. In the next step, I'll present to you the second question, and we'll solve the second question in 2 different methods. Okay. In the second question, we have in the drawing quarter circle AOB. Side OB equals to 2 units, AD equals to DO. Inside this quarter circle, we have this right triangle that is described by the quarter circle, the right triangle CDB. Angle CDB equals to 90 degrees, and we want to find out the area of the blue right triangle, triangle CDB. So we start with the first method, because of the fact that we have here a quarter circle. It means that point O is the center of the quarter circle, and also angle AOB equals to 90 degrees. And here the radius of this quarter circle is OB, that is 2 units, but the radius it is also AO, that is also will be equal to 2 units. So we can write down here that the radius AO equals to the radius OB, that is equal to 2 units. AO equals to OB equals to 2 units, that is the radius of the quarter circle. Okay? So AO equals to AD plus DO. AD plus DO equals to AO. But if we define AD as X, then DO will be also equal to X because of the fact that they are equal to each other. So in conclusion, we found out that X plus X, that is 2X, equals to 2 units. If we divide this equation by 2, and we get that X equals to 1 unit. So here AD that is equal to X, it is equal to 1 unit, and DO that is also equals to X, it is also equals to 1 unit. In the next step, we will complete the quarter circle to a circle. So I completed the quarter circle to a circle, and we'll extend the radius BO by a straight line until it touches the circle. In this point, point P, we define the touching point of the extended BO on the circle as point P. Point O is the center of this circle. Point P is the point of the circle itself. Therefore, OP is the radius of this circle, that is equal to 2 units according to what is given as the question. We extended the radius PO by straight line, so BP is also a straight line. And because of the fact that the straight line BP passes through the center of the circle, that is O, PB is the diameter of the circle. Any chord that passes through the center of the circle must be the diameter of the circle. Therefore, PB that passes through point O, that is the diameter, the center of the circle, it is the diameter of the circle. PB is the diameter of the circle. In the next step, we'll extend side CD by straight line until it touches the circle. Okay? So, we'll extend side CD by a straight line until it touches the circle. So, suppose that when we extend the straight line CD by a straight line, it will touch the circle at this point, and we'll define the touching point of the extended CD with the circle as point X. Okay? Actually, we created here peripheral angle BCP. This is a peripheral angle because it touches the circle on point B, it touches the circle on point X, and the vertex is at point C. So we created here peripheral angle BCX that is equal to 90 degrees according to what is given us in the question. So peripheral angle BCX equals to 90 degrees. We write it down. Peripheral angle BCX it is equal to 90 degrees according to what is given us in the question. Okay? But we have the rule that any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. And the diameter of the circle is PB. I repeat again, according to the rule that any peripheral angle that is equal to 90 degrees, we get that this peripheral angle BCX that is equal to 90 degrees, it must rest on the diameter of the circle that is PB. And here, peripheral angle BCX that is equal to 90 degrees, it is not rest on the diameter that is PB. Therefore, we can conclude from it that point P must merge with point X, must merge with point P, and we have here only one point. In order that the peripheral angle BCX that is equal to 90 degrees will rest on the diameter that is PB, point X must merge with point P. That is to say, it means that the straight line that we extended side CD by straight line, that straight line must pass through point P. This is the only way that the peripheral angle BCP will rest on the diameter that is BP. Here, peripheral angle BCP must rest, must pass through point P, it must touch point P, and this is the only way that the peripheral angle BCP that is equal to 90 degrees will rest on the diameter that is PB. Otherwise, if the extended side CD will not touch point P, it means that we have here peripheral angle that is equal to 90 degrees, and it is not rest on the diameter. That is contradiction to the rule that any peripheral angle that is equal to 90 degrees must rest on the diameter. So this peripheral angle BCP must rest on the diameter that is PB. Therefore, peripheral angle BCP must pass through point P. It must touch point P. In order to this peripheral angle will rest on PB, it must touch point P. Okay? So we actually arrive to the conclusion that angle BCX, it is actually equals to angle BCP because of the fact that point P, point X merge with point P. Okay? And here PB is the diameter of this circle, therefore it is absolutely a straight line, and we have the rule that the sum of the angles on one side of a straight line equals to 180 degrees. So if we focus on the upper side of the straight line PB at point O, the sum of the angles here must be equal to 180 degrees. So which angles we have here? We have 90 degrees plus this angle. In total, the sum of those two angles must be equal to 180 degrees. So therefore, this angle must be equal to 90 degrees in order to complete the sum of the angles at point O on the upper side of PB to 180 degrees. This angle must be equal to 90 degrees. Okay? So we actually have here the right triangle, triangle PDO, POD. In the right triangle POD, in the right triangle POD by PB by PT is the abbreviation for Pythagoras theorem. In the right triangle POD by PT, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is PD, therefore the square of the hypotenuse is PD squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to DO squared plus PO squared. Okay? So according to the Pythagoras theorem on the right triangle POD, D square equals to DO square plus BO square. So PD square equals to DO square. DO equals to 1, so DO square is 1 square, that is 1, plus PO square. PO equals to 2 units, so PO square is 2 square, that is 4. So in conclusion, I found out that PO square equals to 1 plus 4, that is 5. We take out, actually it is PD square. PD square equals to 1 plus 4, that is 5. We'll take a root from this equation. We'll get that PD equals to a square root of 5 units. PD equals to a square root of 5 units. And I tell that PD equals to a square root of 5 units. In the next step, we will focus on the right triangle, triangle DOB. In the right triangle, triangle DOB by PT, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, the hypotenuse is dB, so dB squared must be equal to DO squared plus OB squared. So according to the Pythagoras theorem, in the right triangle DOB, dB squared equals to DO squared plus OB squared, so dB squared equals to DO squared. DO equals to 1, so DO squared is 1 squared, that is 1, plus OB squared. OB is 2, so OB squared is 2 squared, that is 4. So in conclusion, we found out that dB squared equals to 1 plus 4, that is 5. Here we take a root out of this equation and we get that dB equals to the square root of 5 units. dB equals to the square root of 5 units. In the next step, we'll extend the radius, AO by a straight line. Until it touches the circle. At this point, we'll define the touching point of the extended AO and the circle as point Z. Okay? In the next step, I will present to you rule number 1 that I've already mentioned in the past. rule number 1 deals with two chords that intersect with each other inside the circle. So this is rule number 1. According to rule number 1, we will get that if we have this circle, and inside this circle we have two chords. We have chord AB, this is chord AB, that intersects with chord CD, this is chord CD, and the intersection point is happening at point O. Point O is the intersection point of chord AB with chord CD. So if this is the data that has been given to us, then according to rule number 1, the following equation is true, that AO times OB equals to CO times OD. Repeat again. AO times OB equals to CO times OD. Okay. We actually can implement rule number 1 in our drawing, because in our drawing we have chord AZ that intersects with chord CP at point D. Again, chord AZ intersects with chord CP at point D. I'll write it down. Chord AZ intersects with chord CP at point D. Point D is the intersection point of chord AZ with chord CP. Okay, so therefore according to rule number 1, we get that AD times DZ equals to PD times DC. I'll repeat again. We get that according to rule number 1, AD times DZ equals to PD times DC. Okay? So here AD equals to 1, DZ equals to 1, and here O is the center of the circle, Z is the point of the circle itself. So this is exactly the definition of a radius. That is to say, OZ is the radius of this circle, that is also the radius of the quarter circle, that is equal to 2 units. Okay, now we'll find out the depth of DZ. DZ, from the drawing it is very easy to see that DZ equals to 1 plus 2, that is 3. dz equals to 3, and it is equal to PD. PD equals to square root of 5 units times DC. DC is the missing line segment. So in conclusion, we found out that three equals to square root of 5 times DC. Here we divide this equation by square root of 5, and we get that DC, the missing line segment, equals to 3 over square root of 5 units. Here DC equals to 3 over square root of 5 units. In the next step, we will implement the Pythagoras theorem on the right blue triangle, triangle CDB. This is the triangle that we are looking for. We want to find out the area of this triangle, the blue right triangle CDB. So we'll implement the Pythagoras theorem on the right triangle CDB. According to the Pythagoras theorem on the right triangle CDB, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is dB, therefore the square of the hypotenuse is dB squared, and it is equal to the sum of the squares of the perpendiculars. That is to say, it is equal to DC squared plus CB squared. So, I repeat again. In the right triangle, triangle DCB, according to the Pythagoras theorem, dB squared equals to DC squared plus CB squared. So here, dB squared equals to DC squared. DC is 3 over square root of 5, so this C squared will be equal to 9 over 5 plus CB squared. Plus CB squared, CB is the missing line segment. dB equals to square root of 5, therefore dB squared is square root of 5 squared, that is 5. So we'll substitute, here we'll substitute dB squared by 5. 5 equals to 9 over 5 plus CB squared. Here we'll substitute 9 over 5 or 9/5 from this equation, and we get that CB squared equals to 5 minus 9 over 5. Here we'll multiply 5 by 5 and then we'll divide it by 5 in order to have a common factor of this expression, and we'll get that CB squared equals to 5 times 5 is 25, so it is 25 minus 9 over 5. 25 minus 9 is 16 over 5. So if we really found out that CB squared equals to 16 over 5. Here we'll take a root out of this equation and we'll get that CB equals to the square root of 16, that is 4, over square root of 5. So in conclusion, we found out that CB equals to 4 over square root of 5. You can write down here that the drawing that CB equals to 4 over square root of 5. In the next step, we will find out the area of the green, of the blue right triangle, triangle DCB, and the area of this right triangle, triangle DCB equals to the base of the triangle, that is DC, times the I to the base, that is CB, over 2. I repeat again, that the area of the blue right triangle DCB equals to the base of the triangle, that is DC, times the I to the base, that is CB, over 2. So DC equals to 3 over square root of 5 units, CB equals to 4 over square root of 5 units, all divided by 2. Okay, so we got here that 3 times 4 is 12, square root of 5 times square root of 5 is 5, times 2. So here we have 12 over 2 is 6, and then the denominator of what is left is only 5. So in conclusion, we found out that the area of the blue right triangle DCB, according to the first method, equals to either 6 over 5 square units, or in terms of numbers, it is equal to 1.2 square units. We finished with the first method. In the next step, I will present to you the second method. We know that this angle A will be equals to 90 degrees because it is a quarter circle. We have already found out that AD equals to 1 unit, DO also equals to 1 unit, OB is the radius of the quarter circle that is equal to 2 units, and AO also equals to 2 units. We complete the quarter circle to a circle. We'll extend the radius OB by a straight line until it touches the circle. At this point, we'll define the touching point of the extended line segment OB in the circle as point P. O is the center of the circle, P is the point of the semicircle itself, therefore PO is the radius of the semicircle that is equal to 2 units. We have already found out that this angle equals to 90 degrees. Here we will extend side CD by a straight line. We have already found out that when we extend side CD by a straight line, it must touch point P. It must pass for point P. In the first method, okay, so we have here, we've already found out that PD, the hypotenuse PD equals to the square root of 5 units, and the hypotenuse OB of the right triangle OBD also equals to 5, square root of 5 units. We define angle OBD is theta. So this angle OBD equals to theta, angle DOP equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta in order to complete the sum of the angles in this right triangle OBD to 180 degrees. This angle must be equal to 90 degrees minus theta, because 90 degrees minus theta plus theta is 90 degrees. And 90 degrees plus 90 degrees is 180 degrees. So if we focus on the big right triangle BCP, this angle equals to 90 degrees, this angle equals to theta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta for the same reason, exactly like this triangle. In order to complete the sum of the angles to 180 degrees, this angle must be equal to 90 degrees minus theta. Okay? In the next step, we prove that the right triangle POD is similar to the right big triangle PCB. So why those two right triangles are similar to each other? We prove that the right triangle POD is similar to the right big triangle, triangle PCB. Why those two right triangles are similar to each other? First of all, we have those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So angle POD equals to angle PCB, and they are both equal to 90 degrees, therefore they are equal to each other. I'll repeat again. Angle POD equals to angle PCB equals to 90 degrees. In addition, we have this angle is a common angle that belongs to both triangles, so this angle equals to itself. So angle DPO equals to angle CPB is equal to theta, so it is a common angle that belongs to both triangles. Here, repeat again, angle DPO equals to angle CPB, that is equal to theta, it's a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees and theta, therefore they are equal to each other. So this angle PDO equals to this angle that is actually angle PBC, and they are both equal to 90 degrees minus theta, therefore they are equal to each other. And repeat again, angle PDO equals to angle PBC, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually found out that all three angles of triangle POD can go into all three angles of triangle PCB, therefore triangle POD is similar, this is the sign of similar, to triangle PCB according to angle similarity rule. And from the fact that the two right triangles are similar to each other, we will conclude that the following relationship exists between their sides. We will conclude that PD over PB equals to DO over CB, and it is equal to PO over PC. So from the fact that the two right triangles are similar to each other, we conclude that PD over PB equals to DO times CB equals to PO over PC. So here PD equals to square root of 5 units over PB. PB equals to 2 plus 2, that is 4, and it is equal to DO. DO equals to 1 over CB. CB is the missing line segment, so we leave it as it is, and it is equal to PO. PO is 2 over PC. PC equals to square root of 5 plus DC again. PC equals to square root of 5 plus DC. So in conclusion, we found out that square root of 5 over 4 equals to 1 over CB equals to 2 over square root of 5 plus DC. We create the first equation. Those two expressions are equal to each other. That is to say, square root of 5 over 4 equals to 1 over CB. Here we cross multiply this equation, equation number 1, and we get that according to equation number 1, square root of 5 times CB equals to 4. We divide this equation by square root of 5, and we get that according to equation number 1, CB equals to 4 over square root of 5. So if we found out here that CB equals to 4 over square root of 5, and write it here down. In the next step, here, square root of 5 over 4 equals to 2 over square root of 5 plus DC. So write it down. According to equation number 2, square root of 5 over 4 equals to 2 over square root of 5 plus DC. Okay, here we cross multiply this equation, equation number 2, and we get that according to equation number 2, square root of 5 times square root of 5 plus DC equals to 4 times 2 is 8. Here we'll open the brackets on this side of equation number 2, and we get that according to equation number 2, square root of 5 times square root of 5 is 5, and plus square root of 5 times DC equals to 8. Here we subtract 5 from this equation, equation number 2, and we get that according to equation number 2, square root of 5 times DC equals to 8 minus 5, this is 3. Here we divide this equation number 2 by square root of 5, and we get that DC equals to 3 over square root of 5 units. So DC equals to 3 over square root of 5 units. So right here, that DC equals to 3 over square root of 5 units. Now it is very simple to find out the area of the right blue triangle, triangle DCB. The area of this triangle equals to the base of the triangle, that is DC, times the height to the base, that is CB, over 2. Okay, I will repeat again. The area of triangle DCB equals to the base of the triangle, that is DC, times the height to the base, that is CB, over 2. So the area equals to DC, that is 3 over square root of 5, times CB, that is 4 over square root of 5, all divided by 2. So it is actually equals to 3 times 4, that is 12, square root of 5 times square root of 5 is 5, times 2. Here 12 times 2 is 6, and in the denominator we left only with 5. So the area of the right blue triangle, triangle DCB, equals to either 6 over 5 square units, or in terms of numbers, it is equal to 1.2 square units. We finish with the second method. In the next step, I will present to you, I will summarize the lecture. We start with the first question, of course. So we have here right triangle, triangle ABC. Side AB equals to 8 units, and we also know that BC and AC are integers. Inside this right triangle, triangle ABC, angle ABC equals to 90 degrees. Inside this triangle, triangle ABC, we have this circle that is inscribed by the right triangle ABC, and we want to find out the radius of this circle that is inscribed by triangle ABC. So first of all, we define side BC as A and side AC as B, and we implemented the Pythagoras theorem on the right triangle, triangle ABC. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, AC square equals to AB square plus BC square. AC square equals to AB square plus BC square. According to our definition, AC equals to B, so AC square is B square. AB equals to 8, so AB square is 8 square, that is 64, plus BC square, BC is 8, so BC square is 8 square. So conclusion found out that B square equals to 64 plus 8 square. We subtracted 8 square from this equation, equation number 1, and found out that B square minus 8 square equals to 64. We use the algebraic identity that states that A B square minus A square equals to B plus A times B minus A. So we substitute B square minus A square by B plus A times B minus A, and according to equation number 1, this is equal to 64. So it is given us the question that A, C and BC are integers. AC equals to B, BC equals to A, therefore B and A are integers, and we also know that A and B are the lengths of the sides of the right triangle ABC. B is the hypotenuse of the length of the hypotenuse, A is the length of the perpendicular, so A and B as the length, they must be positive numbers. So from one side there must be integers, according to what is given in the question, and from the other side there also must be positive numbers. So from those two things we'll derive that there must be a positive integers. Okay, A and B must be positive integers, and B is a positive integer and A is also a positive integer. Therefore B plus A must be also a positive integer, because when you add a positive integer to a positive integer, the result must be a positive integer. So B plus A is a positive integer, and we know that B is the hypotenuse of the right triangle, and the hypotenuse is always greater than the perpendicular. So B is greater than A. So if we subtract A from this equation, we get that B minus A is greater than 0. So we know that B minus A is greater than 0, that is to say it is a positive number. And because of the fact that B minus A is a positive number, B minus A must be a positive integer, because when you subtract from a positive integer another positive integer, if the result is not a negative number, if the result must be a positive, like in this case, the result must be also a positive integer. Okay, so we know that B plus A is a positive integer, and B minus A is also a positive integer, and B is a positive integer and A is also a positive integer. Therefore B plus A must be greater than B minus A, because when you add two integers together to each other, then the result must be greater than when you subtract them from each other. It is very simple. Okay, and whenever you add two positive integers to each other, the result must be greater than when you subtract the two positive integers by each other. So b plus a must be greater than b minus a. So this column must be greater than the second column. So which possibilities we have that when we multiply two positive integers by each other, the result is 64. There are a lot of possibilities here, so we will write down all the possibilities that the multiplication of two positive integers by each other will give us a positive integer. So here 1 times 64 is 64, 2 times 32 is 64, 4 times 16 is 64, 8 times 8 is 64, 16 times 4 is 64, 32 times 2 is 64, and 64 times 1 is 64. So those are the possibilities that the multiplication of two positive integers will give us 64. There are 7 possibilities here, but because of the fact that this b plus a is greater than b minus a, according to this equation, we'll get that the first column must be greater than the second column. Okay? Here 1 is not greater than 64, therefore this is not possible, so we cancel the solution. 2 is not greater than 34 than 32, therefore we will cancel this possible. 4 is not greater than 16, therefore we will cancel this solution. 8 is not greater than 8, therefore we will cancel this solution. 16 is greater than 4, therefore this is a possible solution. And 32 is also greater than 2, therefore this is a possible solution. And also 64 is greater than 1, that is also a possible solution. Now we will add the two numbers together in order to find out the result. Here b plus a plus b minus a equals to b plus b, that is 2b, and a minus a is 0. So we found out that if we add the two numbers together, the result is an even number, because 2b is an even number. Why? Because b is a positive integer, and when you multiply a positive integer by 2, the result must be an even number. That is to say, it means that if we add the two numbers together, the result must be an even number. So we'll check which solutions met this requirement. Okay, here 16 plus 4 is 20, 20 is an even number, therefore this possibility is good possibility. 32 plus 2 is 34, that is an even number, therefore this is a good possibility. But 64 plus 1 is 65, that is an odd number, it is not an even number, so this solution is incorrect solution. So we left only with two solutions that are possible. A plus b is 16 and b minus a is 4, and the second solution b plus a is 32 and b minus a is 2. Okay? So here, according to the first solution, b plus a is 16 and b minus a is 4. And according to the second solution, b plus a is 32 and b minus a is 2. So here we have b plus a is 16 and b minus a is 4. b plus a plus b minus a will add the equation, the first equation to the second equation. So b plus b is 2b and a minus a is 0. In the other side of the equation we have 16 plus 4, that is 20. So in conclusion we found out that 2b equals to 20. We divide this equation by 2 and we get that b equals to 10 units. So b equals to 10 units, and we have this equation that b plus a equals to 16. We subtract b from this equation and we get that a equals to 16 minus b. And we already found out that b equals to 10, so we substitute b by 10, and we get that a equals to 16 minus 10, that is 6. So a equals to 6 units. Okay, we found out that a equals to 6 units, and b equals to 10 units, according to the first solution, that is to say, the perpendicular A is 6 and the hypotenuse B is 10, and the other perpendicular is 8 units. Okay, so here A equals to 6 units and the hypotenuse B equals to 10 units according to the first solution. According to the second solution, A plus B equals to 32 and B minus A equals to 2. We'll add the two equations together. B plus B is 2B and A minus A is 0. 32 plus 2 is 34, so in conclusion we found out that 2B equals to 34. We divided this equation by 2 and we get that B equals to 34 over 2 is 17. So here the hypotenuse B equals to 17 units, and according to this equation, B plus A equals to 32. We'll subtract B from this equation and we get that A equals to 32 minus B, and we already found out that B equals to 17, so we can substitute B by 17 and we get that A equals to 32 minus 17. 32 minus 17 is 15, so we found out that A equals to 15. A, the perpendicular BC, that is A equals to 15, and B, that is the hypotenuse, equals to 17 units, and AB equals to 8 units, and this is a right angle. So those are the two solutions that are possible. So I draw the two triangles. According to the first solution, AB equals to 8, BC equals to 6, and the hypotenuse AC equals to 10. And according to the second solution, here AB equals to 8 units, it is given us the equation, angle ABC equals to 90 degrees, BC equals to 15, and the hypotenuse AC equals to 17. So inside both triangles we have a circle that is inscribed, and the question is to find out the radius of this circle that is inscribed by the right triangle, triangle ABC. We have to find out the radius of those two circles that are inscribed in those two specific triangles. So in order to find out the radius of the circle that is inscribed by the right triangle, triangle ABC, we will use triangle ABC. That could be any triangle. This is triangle ABC. That could be any triangle. In triangle ABC, the right triangle, triangle ABC, side AB equals to A units, side BC equals to B units, and the hypotenuse AC equals to C units. And here we have this circle that is described by the right triangle, triangle ABC, that could be any triangle. So here, according to rule number 1, that the tangent to a circle is perpendicular to the radius down to its point of tendency. The radius ON is on to the point of tendency, therefore this angle equals to 90 degrees and this angle also equals to 90 degrees. The radius OM is on to the point of tendency, therefore according to rule number 1, this angle equals to 90 degrees and this angle also equals to 90 degrees. So in quadrilateral NOBM we have 1, 2 right angles, therefore the fourth angle must be also equal to 90 degrees. Therefore in quadrilateral MOBM, we have NOBM, we have 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrilateral NOBM as a rectangle, and we know that the opposite sides of a rectangle are equal to each other. So NO equals to BM, but NO equals to R, therefore BM also equals to R. Here, according to the same rule, the opposite sides of a rectangle are equal to each other, we get that OM equals to NB. But OM equals to R, so therefore MB will be also equal to R. So we found out that quadrilateral ONBM is not a rectangle but a square. And here, what is the length of AN? AN equals to AB minus MB. So AB is A and AB is R, so AN equals to A minus R. Then we found out the length of CM. CM equals to CB, that is B, minus BM, that is R. So it is B minus R. Then according to rule number 2, a tangent to a circle is perpendicular to the radius known to its point of tendency. And at point A, we have two tangents, AM and AC, AN and AC. And according to rule number 2, they are equal to each other. That is to say, AN equals to AN. AN equals to AN, but AN equals to A minus R, therefore AN must be also equal to A minus R because they are equal to each other. Likewise, in the common example in point C, we have two tangents to the circle, tangent CM and tangent CL. And according to rule number 2, they are equal to each other. That is to say, CM equals to CL, but CM equals to B minus 4, therefore CL must be also equal to B minus 4 because of the fact that they are equal to each other. So, the hypotenuse AC, we have AC equals to, the hypotenuse AC equals to AL plus LC. The hypotenuse AC equals to AL plus LC. That is to say, AL equals to A minus R and LC equals to B minus R. AL equals to A minus R and LC equals to B minus R. So AC equals to C according to our definition. So C equals to A minus R plus B minus R. A minus R plus B minus R is A plus B minus R plus minus R is minus 2R. So in conclusion, C equals to A plus B minus 2R. We added 2R to this equation and found out that 2R plus C equals to A minus B. We subtracted C from this equation and we found out that 2R equals to A plus B minus C. We divided this equation by 2 and found out that the radius that we are looking for, R equals to A plus B minus C over 2. Now we can find out the radius of those two circles that are inscribed inside the right triangle, triangle ABC, according to this formula, because this is a general formula. This is a general formula to find out the radius of any circle that is inscribed by a right triangle, triangle ABC. So this formula, I copied this formula here. The radius of any circle that is inscribed by a right triangle, triangle ABC will be equal to A plus B, that is the sum of the perpendiculars, minus the hypotenuse over 2. So in this specific right triangle, we have this circle, and the radius of this circle will be equal to A plus B, that is 8 plus 6, that is 14, minus the hypotenuse, that is 10 over 2. 8 plus 6 is 14, minus 10 is 14 minus 10 is 4, and 4 over 2 is 2. So we found out that the radius of this circle is 2 units. Then we found out the radius of this circle here, the radius equals to 8 plus 15 minus 17 over 2. 8 plus 15 is 23, and 23 minus 17 is 6, and 6 over 2 is 3, according to this formula, of course. So we actually found out that the radius of this circle is 3 units. So in conclusion, the answer to this question is that the radius of this circle that is inscribed by the right triangle, triangle ABC, it will be equal to either 2 units or 3 units. That is the answer to the question. Then I presented to you the second question, and we solved the second question in 2 different methods. Okay? So in the drawing we have a quarter circle, side OB equals to 2 units, AD equals to DO. Inside this quarter circle we have the right triangle COD, angle DCB equals to 90 degrees, and we want to find out the area of the blue right triangle, triangle DCB. So here, because of the fact that AOB is a quarter circle, angle AOB equals to 90 degrees, and the radius of this quarter circle is OB, that is equal to 2 units, and the radius is also AO, and there AO equals to AD plus DO. So if we define AD as X, then DO will be also equal to X. So here X plus X equals to AD plus DO, that is AO, that is equal to 2 units, that is the radius of the quarter circle. So X plus X is 2X. So in conclusion, we found out that 2X equals to 2. We divided this equation by 2 and found out that X equals to 1. So here X AD, that is X equals to 1, and DO, that is also X, is equal to 1. Then we completed the quarter circle to a circle. We extended the radius BO by straight line until it touches the circle at point P. Point O is the center of the circle. Point P is the point of the circle itself. Therefore, PO is the radius of this circle, that is equal to 2 units. And then we extended the side CD by a straight line, and this straight line must pass through point P. Why? Otherwise, if the straight line DC, when we extend it, it's not passing from point P, but other point X, we'll get that we have here a peripheral angle that is equal to 90 degrees, and it is not resting on the diameter. That is a contradiction to the rule that any peripheral angle that is equal to 90 degrees must pass from the diameter, must rest on the diameter of the circle. So in order that the peripheral angle BCP will be rest on the diameter that is PB, it must pass through point P. Therefore, when you extend CD by straight line, it must touch point P. Okay? So that is to say, peripheral angle BCX equals to peripheral angle BCP. That is to say, point X merged with point P. Okay? So in the right triangle POD, according to the Pythagoras theorem, PD square equals to DO square plus PO square. Right triangle POD, PD square equals to PO square plus PD square plus PO square. PO is 1, so DO square is 1 square, that is 1. PO is 2, so PO square is 2 square, that is 2. So we found out that PD square equals to 1 plus 4, that is 5. We took out from this equation and found out that PD equals to a square root of 5 units. Okay, so PD equals to a square root of 5 units. We repeat on the same process on this right triangle, and we found out also that BD is also equals to a square root of 5 units. Okay? Then we extended the radius AO by straight line until it touches the circle at point Z. And then I presented to you rule number 1. According to rule number 1, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. Actually, we can implement rule number 1 in our drawing, because in our drawing we have chord AZ that intersects with chord CP at point D. Therefore, AD times DZ will be equal to PD times DC. Chord AZ intersects with chord CP at point D. Therefore, AD times DZ equals to PD times DC according to rule number 1. AD is 1. DZ is 1 plus 2, that is 3. DZ is 3. DP is equal to 5. So in conclusion, we found out that 3 equals to square root of 5 times DC. We divided this equation by square root of 5 and we found out that the missing line segment DC equals to 3 over square root of 5 units. Here DC equals to 3 over square root of 5 units. Then we implemented the Pythagoras theorem on the right triangle DCB. Here DB square will be equal to DC square plus CB square. The right rule triangle DCB. DB square equals to DC square plus CB square. So here DB square equals to DC square. DC is 3 over square root of 5, so DC square is 9 over 5 plus CB square. DB equals to square root of 5, so DB square is 5. So 5 equals to 9 over 5 plus CB square. We subtracted 9 over 5 from this equation and found out that CB square equals to 5 minus 9 over 5. Here we multiplied 5 by 5 and then we divided by 5 in order to have a common factor with this expression, and we found out that CB square equals to 25 minus 9 over 5. 25 minus 9 is 16, so here CB square equals to 16 over 5. We took out of this equation and we found out that CB equals to the square root of 16, that is 4 over square root of 5. So here CB equals to 4 over square root of 5. Now it is very easy to find out the area of this right triangle DCB. It is equal to the base of the triangle that is DC times the height of the base that is CB over 2. Here the area of the right triangle DCB equals to the base that is DC times the height that is CB over 2. DC is 3 over square root of 5 units. CB is 4 over times square root of 5 units, all divided by 2. So 3 times 4 is 12. Square root of 5 times square root of 5 is 5, and also we multiplied by 2. So here we will have 12 over 2 is 6, so in the numerator we have 6, and in the denominator what is left is only 5. So in conclusion, we found out that the area of the blue shape of the right triangle DCB equals to either 6 over 5 square units, or in terms of numbers it is 1.2 square units. We finished with the first method, then I presented to you the second method. According to the second method, we know that this angle equals to 90 degrees, this angle also equals to 90 degrees, AD equals to 1 unit, DO equals to 1 unit. We completed the quarter circle to a semicircle. We actually extended line segment CD until it touches the circle at point P. We have already found out that when you extend the straight line CD by straight line, it must touch point P. It must pass for point P. Okay? According to the first method. According to the first method, we found out that the hypotenuse PD equals to square root of 5 units, and the hypotenuse is here dB also equals to square root of 5 units. PO is 2, OB is also 2. So we defined angle OPD as theta. This angle equals to theta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta. For the same reason, here this angle equals to theta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta in the right triangle PCB. Then we proved that the two right triangle POD is similar to the right big triangle PCB. Why those two right triangles are similar to each other? First of all, those two angles they are both equal to 90 degrees, therefore they are equal to each other. Those two angles they are both equal to 90 degrees one theta, therefore they are equal to each other, and we also have a common angle that is equal, belongs to both triangles, therefore this angle equals to itself. So we actually prove that all the angles of triangle ADB congruent of triangle AOD congruent to all the angles of triangle PCB. Therefore, triangle POD is similar to triangle PCB according to angle similarity rule. And from the fact that the two right triangles are similar to each other, we will derive that PD over PB equals to DC over CB, and it is equal to PO over PC. Okay, so PD is equal to 5, PB is 4, DO is 1, and CB is CB, PO is 2, and PC is equal to 5 plus DC. We derive the first equation, equal to 5 over 4 equals to 1 over CB, because multiplied this equation and found out the square root of 5 times CB equals to 4. We divided this equation by square root of 5 and found out that CB equals to 4 over square root of 5 units. Here CB equals to 4 over square root of 5 units. Then we implemented the Pythagoras theorem on the right blue triangle CDB. Actually we created the second equation from this long equation. We created the second equation, that 4 square root of 5 over 4 equals to 2 over square root of 5 plus DC. This is equation number 2. We also multiplied the equation number 2 and we found out that square root of 5 times square root of 5 plus DC equals to 4 times 2, that is 8. We opened the brackets on this side of equation number 2 and found out that square root of 5 times square root of 5 is 5. Plus square root of 5 times DC equals to 8. We subtracted 5 from this equation and found out that square root of 5 times DC equals to 8 minus 5, that is 3. We divided this equation by square root of 5 and found out that DC equals to 3 over square root of 5. Now it is very easy to find out the area of the blue shape of the right triangle DCB. It is equal to the base of the triangle, that is DC, times the height to the base, that is CB, over 2. Again, it is equal to the base of the area of triangle DCB equals to the base of the triangle, that is DC, times the height to the base, that is CB, over 2. DC equals to square root of 3 over square root of 5. CB equals to 4 over square root of 5, all divided by 2. 3 times 4 is 12, and square root of 5 times square root of 5 is 5, all divided by 2. So we have 12 over 2 is 6, on the numerator we have 6, and the denominator of what is left is only 5. So we actually found out that the area of the blue right triangle DCB equals to either 6 over 5 square units, or in terms of numbers it is equal to 1.2 square units. So we arrived to the same result in both methods. Okay, thank you very much.